Okay, so I want to talk very, very briefly about these things called eigenvalues and eigenvectors, because I think whilst you would have done a lot of questions on these things in the first year, and there's a lot of things available on the internet, there's not necessarily kind of what they mean, anything which is on what they mean, and you may not have necessarily either remember, or because it wasn't taught like that, what eigenvalues and eigenvectors actually mean in terms of what we want to get out of them. Okay, so basically the easiest way to explain this is if we've got a matrix A, okay, and this could be a table of numbers, and it's literally like a table of numbers, right? And it could be as big as you like, all right? As you know, it's always got to be a square matrix. But if you like, this matrix has got a lot of impurities in it, because of course a matrix is just a table of numbers where these numbers have some kind of meaning and some kind of relation to each other in them. But just looking at this table of numbers can be incredibly difficult to kind of see what's going on. Okay, you've got a load of numbers in front of you. You can't necessarily tell anything about the matrix just by looking at this table of numbers. So where eigenvalues and eigenvectors come in, by the way, eigenvectors just come from eigenvalues. So we just consider eigenvalues for the moment. Where these eigenvalues come in is basically they can boil this matrix down into just a handful of numbers. And quite a lot of the time, and those numbers are called eigenvalues, and quite a lot of the time those numbers, all we're interested in is whether they're positive or negative, just the sign of them, and also whether they're equal to each other. So we're not even necessarily bothered about the value explicitly as such, and just looking at the signs of these eigenvalues and just looking at the, whether they're equal to each other can tell us an awful lot about this matrix. Okay, so the way which I like to think of it, in Australia, there's other places around the world, I think South America is another place as well, but in Australia they mine this ore called bauxite, and it's found at the surface of the earth, okay, in the earth's crust, and they come along with their little diggers, okay, and they essentially scoop out this bauxite, okay, and this bauxite is basically an ore, okay, and they scoop it out, and then basically they take it to a refining plant, okay, and they essentially just burn off all of the impurities, okay, and then what they're left with is a nice shiny steel of aluminium. That's gold, aluminium, okay, and that's basically like the purity at the end of it. So if you want to draw an analogy to it, this bauxite is like our matrix. It's got everything in it. It's got all of the impurities. It's basically like bauxite is an orange ore kind of thing. It's very sandy, very orange ore, and that's our matrix. It's got all the impurities in. Okay, you can't necessarily tell that there's aluminium contained inside this ore. And then what you have to do is you have to do a process and refine it, burn off all those impurities, and then what you're left with is a nice shiny shiny piece of aluminium. Okay, so this is exactly the same thing we're doing here. So we're taking this matrix and we're doing something to it, and then from that we're getting the eigenvalues out, and that's, if you like, the eigenvalues are a nice shiny piece of aluminium. So what I'm actually going to do is I'm going to consider, so the idea is, let's consider first of all the idea is that we need to solve this equation. So it's A times lambda, so our matrix A times lambda, okay, will be equal to, sorry, that wasn't quite right, it was ringing bells for me. It's not A times X. Basically we have our matrix A, and we multiply it by some vector X, and that vector is just going to be all of our variables contained in it. So A is an n by n matrix. This only works for a square matrix. Okay, so A is going to be an n times n by n matrix, and X is going to be all our variables, and there's going to be n variables, and it's going to be a vector of those, putting them in a vector, just a list of numbers. Okay, well, the idea is that that's going to be the same as just multiplying our vector, so our vector of variables, by some constant, and we're going to call that lambda. Okay, and lambda here will correspond to our eigenvalues. So this is basically the equation that we need to solve. The idea is that we can basically take this matrix and we can boil it down into just a set of numbers, a set of constants, and those numbers are called eigenvalues. So this equation solves. We've got our matrix A here multiplied by our vector X, and that's quite a difficult thing to solve. Well, what we can do is we can boil it down, and we can basically represent this matrix A as just our eigenvalues, and we can solve the same equation. So they're literally the same thing. Okay, so hopefully that makes a bit of sense. And then we can do a bit of rearranging. So let's take the lambda x onto this side, so lambda x, and that's going to be equal to 0. Let's do a bit of factoring. Okay, so we take an x out basically, so we've got a minus lambda I times x. Notice the use of using an I now times by lambda, because what we're doing is one matrix take away another matrix. Now I've just said that lambda is just some number, alright? So I'm doing a matrix A take away some number. Well, I can't do that. I have to do a matrix take away another matrix. I can't do say like a B, C, D. I can't do that take away say like 3. Alright, it has to be a matrix of some description, something like that. Okay, so that's just all I'm doing. Okay, and of course lambda is just one number. Okay, well the matrix representation of the number 1, so I'm doing this number multiplied by 1 effectively. Well, the matrix representation of 1 is just the identity matrix. Alright, so I'm just taking this now and I'm solving it. Well, that implies that either, hopefully you can see this, either a minus lambda I, what's going on? My thing's disappearing. Okay, let's hope this works now. So that implies that either the first bracket equals 0, so a minus lambda I equals 0, or of vector x equals 0. Well, we always say that our vector x is not consisting of 0 elements. Okay, all our vector x is non-zero. Okay, the reason why is because it's not necessarily useful if our vector, if our vector x is just a 0 matrix, then that's just considering a very, very specific case. Okay, it's just all the elements inside that vector are just all 0. That's a very, very specific case. So in general, we want to consider a case when it's not all 0, because of course there are infinitely many numbers. 0 is just one of those numbers. So it's more likely that we're going to have a non-zero vector. Okay, so we just take x is not equal to 0 as convention. Okay, well the only way that this can happen is if the matrix is non-singular. Okay, that's the only way that it can happen. Sorry, let me just think about that. Yeah, so let me just come back to that. The idea is that this thing can't have an inverse. Okay, so in other words, the easiest way of just saying it's easy just to say it. Okay, it can't have an inverse. There's no inverse that exists. In other words, it's singular. Okay, and the only way that is true is if the determinant of this is equal to 0. So just consider this as one matrix. Well, if it's equal to 0, then therefore it doesn't have an inverse. Okay, and the way of saying that is that this doesn't, the determinant of that matrix is equal to 0, then it doesn't have an inverse. So this is basically the system which we want to try and solve. So let's say if we have a matrix, I'm just going to consider a 2 by 2 case. Let's say if we have the matrix 1, 2, 8, 1. Alright, and I want to find the determinant of this. So in other words, I want to find the determinant of a minus lambda I. Okay, and I want to set that equal to 0 and find out what I get. I'm going to set up with an equation and see what I get out of it. So let's do this. So I want to do a minus lambda I. So I want to do 1, 2, 8, 1. Then I want to do minus lambda I. Well, lambda I will just be lambda times 1, 0, 0, 1. It's a 2 by 2 case, and I want to set that equal to 0. Okay, and then do the same thing. So let's do the next thing. So we've got 1, 2, 8, 1. Minus, multiply this by lambda, so I've got lambda 0, 0, lambda. Okay, and I want to set that equal to 0. And then finally, next step, I want to do 1 minus lambda, 2 minus 0, 8 minus 0, and then I've got 1 minus lambda here. I'm going to set that equal to 0, and I'm going to take the determinant of all these things. Okay, so if I take the determinant of it, remember a 2 by 2 matrix is just this element multiplied by this element, so 1 minus lambda multiplied by 1 minus lambda, okay, minus this element times this element, which of course is 16, set it equal to 0, do a bit of expanding, so I get 1 minus 2 lambda plus lambda squared minus 16 equals 0. Okay, do a little bit of simplification again, so I've got lambda squared minus 2 lambda minus 15 equals 0. Try and solve that directly. Just got a quadratic there, so what have we got? 5 and 3 looks like it might do it. Minus 5 plus 3. Lambda minus 5. Lambda plus 3. Does that work? Equals 0. So yeah, they add together to make minus 2. Multiply together to make minus 15. Cool. So that means that I've got now 2 eigenvalues. These are my eigenvalues. Lambda is just my eigenvalue. So lambda 1 equals 5. And lambda 2 equals minus 3. Okay, now I can look at those two eigenvalues, all right, and I can basically talk about, because these are two opposite signs, all right, I can talk about certain properties which now this matrix A, remember, which is 1, 2, 8, 1, has. So if I just write this up here, so I've got lambda 1 equals 5, lambda 2 equals minus 3. So because they have different signs, then that means that A has a certain property, and we talk about that a little bit later. So for example, go and have a look at my ODE video. This is very much kind of an appendix to the ODE's video, as kind of a reminder, and sort of look and see the case where they're both real values, one's positive, one's negative, okay, and see what kind of, what's known as equilibrium point, which is basically where the function which we're considering, the set of equations that we're considering, where the derivatives are equal to 0, so a stationary point, okay, and that will tell us a certain thing about those stationary points and the trajectories coming into that stationary points, just by looking at eigenvalues. Okay, so that's a really useful application, because differential equations are really, really difficult to solve sometimes, and just by looking at eigenvalues we can get all the information that we could possibly need. Okay, and then from this one we can form these things called eigenvectors. Now an eigenvector is just simply a set of values, which when we multiply by these two numbers here, it basically forms a straight line. Okay, and we're not necessarily bothered about the direction of that straight line, we're just basically saying all the different numbers which can multiply by these two eigenvalues that we can get. So, okay, so how are we going to solve now an eigenvalues and eigenvectors? Well, we have to basically solve a system of linear equations in order to get this. Okay, and what we basically need to solve is ax equals lambda x now. Remember the thing which we started with? This was the thing that we started with, right? And we now basically need to solve this equation. Now we know sort of certain values of lambda. We've got two values of lambda. We now need to solve this. Well, first of all, we just want to talk now about what x is, because we kind of hinted to it, but we haven't actually defined it explicitly. Well, x is just our variables, right? The number of variables that we've got. So we've got two equations, therefore we've got two variables. And I'm just going to call them x and y. Okay, so those are our two values. And then we've got a, which of course is our same matrix as before, so I'm going to write it over here. So we've got a, which is 1, 2, 8, 1. And now we've got lambda, and we're going to have to test them for both lambda. So we've got lambda 1 equals 5, and lambda 2 equals minus 3. Okay, so now we've got everything we need to solve this equation. All right, so in other words, what we want to do is we've said what that x is just a vector, x, y. We want to actually find what that vector is, because that is going to give us the eigenvector. Okay, so let's solve this equation for, first of all, lambda 1 equals 5. All right, so we've got a, which is 1, 2, 8, 1, multiplied by xy, and that's going to be equal to 5 lots of xy. Okay, and then we just basically, and then I'm going to write actually the same thing out for lambda 2. So lambda 2 equals minus 3. Okay, so we've got the same thing, 1, 2, 8, 1. I'm going to multiply that by our variables, x, y, is equal to, this time, minus 3 times x, y. All right, and then when we just expand these two things out, so I'm actually going to make this a little bit smaller and write it over this left-hand side, if it works for me. So just keep that in mind, in other words. So put it over there. Okay, so I'm going to expand out the lambda 1 equals 5 one first. So I'm going to end up with 1 times x, x plus 2 times y, so 2y, and that's going to be equal to 5x. Hopefully you can see where that comes from. And then I've got 8x plus y is going to be equal to 5y. Okay, so that's the system of equations that I need to solve now for lambda 1 equals 5. Lambda 1 equals 5. So I need to try and solve that equation. Okay, and if I solve that equation, let me just have a look at the answers. Yeah, so what I'm basically going to do is I'm going to take 1 and I'm going to sub it back into 2. Because basically all I just want, I'm not going to be able to get like a specific number for x and y, but that's fine, because x and y can take any values, and I'm going to show you why that should be true. So for lambda 1, I can basically form the eigenvector just by taking the first equation and rearranging it, so I end up with x equals 5x minus 2y, okay, and then subbing this back into 2, so in 2, I end up with 8 lots of x, which is 5x minus 2y, okay, plus y is equal to 5y. Expand this out, so we get 40x minus 16y plus y equals 5y. All right, do a little bit more rearranging. So I get 40x minus 15y equals 5y. A little bit more, so I end up with 40x, take the y over to the right hand side, and I end up with is equal to 20y. Okay, and divide both sides, this side by 40, so I end up, or this side by 20, makes a bit more sense. So I end up with 2x equals 1y. Okay, does that make a bit more sense? So basically what I've got now is a relationship of x and y, because remember, x and y can take any value I like. Okay, it's just going to be an eigenvector, it's going to be a straight line. This is what this means. So y is equal to 2x. It's literally like just plotting the line y equals 2x on the graph, except now it's going to be a vector, okay, because these are all the values that x and y can take. You can put anything in, and as long as they satisfy that, okay, and that is going to correspond to our eigenvector, or I'm going to call it x1. No, I'm going to call it u1, actually. That's my eigenvector. Okay, so this is just all the values that x and y can take, and of course it can be positive, but it can also be negative as well. Now, a lot of the time, I'm not really interested. The reason why we can use this is because all I'm interested in is how u1 will relate to u2, and I'll work out u2 just now, actually. So I've got 1, 2, so this is for lambda 2 equals minus 3. So I've got 1281 times xy, same thing as before, equals minus 3 lots of xy. Okay, so that then implies that I've got x plus 2y equals minus 3x, and then I've got 8x plus y equals minus 3y. Hopefully that's right. Call that one 1, call that one 2. Okay, now what I'm going to do is the same thing. I'm going to rearrange 1, and I'm going to get x equals minus 3x minus 2y. Okay, and I'm going to put that back into 2. So I end up with 8 lots of this lot. Now I'm just going to do it directly. So I'm going to end up with minus 24 lots of x. Okay, what we got? Minus 16 lots of y plus y. So that's just 8 times by this thing here. Okay, which gives me that. And then I've got plus y is equal to minus 3y. And then I'm going to rearrange, put the x is on one side, the y is on the other side. So I get minus 24x, 74x. That's minus 15. So when I take it over to the other side, I'm going to end up with 12y. All right, and then I'm just going to divide by, I'm minus, no, I'm going to stick with the minus here, actually. I'm going to divide by 12, so I end up with minus 2x equals y. So now what I get is I get the graph equation y equals minus 2x, effectively, so it goes down like this. So it's actually going to be the exact opposite of this one. And this now is u2. So I've now formed my eigenvalues and eigenvectors. Okay, I'm just going to make this a little bit smaller now, and hopefully I can fit it all in. So I've now got my two eigenvectors. Now, a lot of the time, we're only interested to see how these two eigenvectors correspond to each other. And like I say, I'm going to link it back to ODEs and show that actually these eigenvectors will tell us exactly what our phase plane is going to look like. So we don't even have to solve the equation. We can just find eigenvectors and eigenvalues. These are relatively easy. You know, I think the hardest thing is find the determinant of a matrix, but you know, if you can do that, you're pretty okay. You know, 2 by 2 determinant is pretty straightforward. 3 by 3 is pretty straightforward as well. But if you can find the determinant, nice, easy thing. It's much easier than finding general solutions of an ODE. So this is why we basically find, you know, this is how eigenvectors and eigenvalues are pointed. So basically what we've done is we've taken our matrix A, and we've boiled it down into just basically these two vectors, effectively. Here we've got eigenvalues, which tell us useful things, but we've also got eigenvectors now, and these eigenvectors are like a graphical representation. Sometimes if you can see something, it makes a hell of a lot more sense than just having a load of algebra in front of you and ending up with a number at the end, and quite a lot of the time you don't even know what that number means. Whereas if you can actually see what's going on and visualize what's going on, this is a really nice application of that with these eigenvectors, then suddenly it makes a lot more sense. And like I say, in the case of ODEs, we don't even have to try and solve an ODE. We can just look at this kind of approach, finding the eigenvalues, then finding the eigenvectors, and then seeing what's going to happen in each case. And that will actually tell us, you know, with the lines and things, and that will actually tell us an awful lot, or hell of a lot more than just trying to solve an equation, okay, about what the equations are doing.